Okay, so like I said, so last time we were discussing pure substances, mixtures, etc. So now I want to look at another way to classify matter, and that's just through the basic state. Now the most common states I'm sure you're familiar with, solids, liquids, and gases. Of course there are some other weird ones like a plasma, which we won't really discuss in this class, but the basic ones are solids, liquids, and gases. So I kind of want to describe, first we'll just use water as an example, and then we'll try to draw some, what's the word? Draw some analogies, I guess, out of water and see what we can learn about a solid, a liquid, a gas, just from the way that water behaves. So I'm going to draw it here on the board, but so water. So solid water is ice, right? So let's say I had an ice cube, for example, okay? Well, in a solid, all the particles are packed in nice and tight like this. Okay, so they're all packed in really tight, but they are actually moving. You might recall I told you last time that when things get hotter or colder, the reason they're getting hotter or colder is the amount of motion they have, right? So if they have more motion, they therefore have the more kinetic energy, and they're warmer. So as things get colder, they have less motion, right? So same thing here. So these atoms, or well, actually not atoms in this case, these actual molecules, they are moving, but they're not like moving past each other. All they're doing is kind of vibrating a little bit. Okay, kind of sitting here, kind of shaking, and going like this. Okay, so even right now, every solid around you, your desk is vibrating, your calculator is vibrating, your body is vibrating. All the atoms are just kind of vibrating, just a little bit like this. Okay, so they are moving, but they're not moving relative to each other, right? So they're not like moving past each other. Okay, now in a liquid, they are also still packed in pretty tight together, but now they are moving relative to each other. So now they are kind of rolling and jumbling and tumbling past each other. So now they are moving around, but they're still packed in pretty nice and tight. So now they are kind of, meandering past one another, right? They're rolling around, kind of rolling around. So both are still packed in tight. So they are still, they are still in here, tight together. They're tight together, and they are touching. But this one's moving past each other. Okay. And then of course in a gas, now they are not touching each other. There's lots of space between them, which is why you can see right through most gases. So and they are way spread out, and they're moving really fast. So they are zipping. Yeah. So your average air, for example, the oxygen and nitrogen are moving, 300-400 miles an hour. They're like bouncing off the walls and the ceilings and off your face. You don't even realize it. Like hundreds of miles per hour. They're going quick. Okay, so let's just think about this. Let me label these real quick. Solid, liquid, and gas. Okay. So solids, I said, they are packed in tight together, right? So they're packed in there, which means their shape is not going to change, right? So they are locked into place, and they're not moving past each other, so they won't change shape. So you won't come in tomorrow morning, then, or on Monday, let's say, and the walls will change shape, or the desks will change shape, or anything, right? Right, because they are locked into place. They're not going to change shape on you. They also then will not change their size or their volume, because they're not going to suddenly spread out and get bigger, and they can't actually get any smaller either, because they're already packed tight together. So there's no room to make them smaller. So their volume won't change either. So they have a definite volume. Okay? So, so they won't change shape. They won't change volume. Again, they're held together, right? They're tight in a nice pattern. And they are moving, but all they're doing is kind of vibrating slowly. So there's vibrating a little bit there. Okay? So they're vibrating. So yes, they have the least amount of motion we'll see out of all of them. Okay, well, liquids still packed in, but now they're moving past each other. Well, if they can move past each other, then their shape can change, right? So you could totally, have water, and you can make it, round in a round glass or square in a square glass, right? So they'll move around and they'll change the shape to whatever your container is you put them in. But they will not change volume. Their volume is set. So again, you can't get a liquid and spread it out. Spread it out, for example. Let's say you have a 2-liter bottle of Coke. You can't suddenly make it into 3 liters, right? It always stays 2 liters, right? It stays the same volume. And also, again, as far as going smaller either, again, they're already packed in as tight as they can be, pretty much. So you can't make it, 1 liter Coke out of 2 liters of Coke. So the volume won't change, but the shape will change. Okay. Again, like I said, they will, of course, they'll match up with their container. Now they are together, but unlike this, where all they're doing is vibrating, now they are actually, like I said, rolling, right? They're moving past each other. As you can imagine, this is kind of like I don't know, it's a big old jar of marbles or something, right? And the marbles are able to roll past each other. But in this case, the marbles, they are all, glued together, and they're not able to move past each other. So here they are able to roll around. Okay. And then, of course, in the gas, I said they are way far apart, right? So they're really spread out, and they are spread out uniformly. So you won't have like a big cluster of the gas over here in this side of the room, and you guys in the back, you're all suffocating and you can't breathe, right? So, yes, evenly spread out all the way, right? Uniformly spread out. So again, of course, that means their shape can change too, right? So you can get a gas and you can totally, put it in a square room, a round room, whatever you want to do, right? And then it'll change shape. So you can totally move them around and make whatever shape you want. And now the volume can change because you can get these, and you can bring them closer together, so have a smaller volume, or you can spread them out more. So the volume will change as well. That makes sense, right? You can change the volume and you can change the shape. And they will take in whatever shape and whatever volume your container is. So yeah, you release a gas. You release a gas into a room or something. Yeah, it'll just it'll fill the room and have whatever shape the room is. Right. So, and of course, again, I said they are moving fast. Right. So they are by far the fastest. They're going hundreds of miles per hour, bouncing all around, all over the place. You don't even know it because they're so small. Okay, so solids, liquids, and gases. Okay, get your chapter 2 handout with you. Hopefully you brought it. I only told you like 47 times. Go on Blackboard and print it. So, take your best guess. A, B, C, D, E. Solid, liquid, or gas. So yeah, have a little gas there. Or have a little gas. Have a guess real quickly, and then we'll compare with somebody around you. Yeah. Please don't have gas if you can avoid it. Please, yeah. Because it will, it will fill the room, take on the shape and the volume of the room, we learned. So don't do that. Again, these are always on Blackboard, so you can print them out and just saves you having to write them down. So, okay, so yeah, quick guess. Solid, liquid, or gas for each of those, and then meet one of your neighbors or find the neighbor and say, hey, what did you get for these? And compare. Oh, yes. Yeah, you have to, because there's only 3. Oh, you more than the same one? No. Nope. Which one are you trying to use more than one?
I don't know. But it fills the volume of the container, but not the shape of the gas.
Yeah, exactly. Yeah, exactly. It fills the whole room or whatever. Yeah, the liquids won't fill the whole room. Yeah. That'd be very bad. That'd be very bad.
I thought liquid would proceed too, but now like, oh wait, it is. It's a good shape.
Okay, so let's look at these real quick. Hopefully you already compared. A, the volume doesn't change, but you can change the shape of it. What's that? Liquids, yes. So liquids, yes, they will change shape depending on your jar, your glass, your container, your bucket, whatever it is. But they won't get bigger or smaller, right, volume-wise. Okay, the particles are moving very rapidly. Gas, right? They will fill the volume of a container. Yes. Yes, why is it so quiet on that one? Not a liquid, right? Your liquid will not fill the room, hopefully, and drown us all. Yes, only gases fill the volume. Okay, has a fixed arrangement, and they're not moving around. Solids, of course. Have particles that are close together, but they are mobile. They are moving. Liquids. A plus, your first A plus maybe. Oh my God, I don't think it's first. Your first of many, hopefully. Okay, so I told you last time that in chemistry we are concerned with the characteristics of the matter as well. Okay, so what kind of properties can you identify about the matter, right? So whatever it is you're studying. So there are two kind of broad classifications of properties. One is called a physical property, and one is called a chemical property. Now, a physical property is a property that you can observe without changing the substance into something else. Without changing its composition, in other words. So I'll say that again. So you can make this observation about the blackboard, let's say, or about your desk, or about a person, and you don't have to actually change that desk into something else, or change that blackboard into something else. So what are some observations you can make that are going to be a physical property? What could you note about a person, or the desk, or your calculator, or that water, or whatever? What could you measure? A glass of water, let's say. What do you notice about the glass of water? Yeah, right. Clear. Yeah, right. Right. Color, right? You notice the color. What else could you notice? You could do all kinds of stuff. The what? Liquid. Yes, it's physical state. Yes.
It's tap water.
Okay, I guess. Okay, sure. Okay, so I hand you a penny and I tell you, okay.
The mass.
The mass. Okay, yes, right. Yes, the mass. You can measure the mass of something.
Diameter.
Oh, yeah, the size, the volume, the diameter, right? Things like that. You can measure all of these kind of things without changing the water into something else. What else could you measure? The pH. Yes, that's a good one. Oh, what? H? What do you mean H? Oh, the age. Oh, yeah. Oh, okay. Yeah, the age. Okay. Yeah. Sure. Good. Okay. You can measure the density. You can measure the melting point. You can measure the boiling point. You can measure all these different things. You can measure the smell. You can measure the taste. You can measure, is it malleable, which means, okay, so can you bend it around, right? All these things you can measure, and that will not change it into a new substance. Now, the one that's always confusing, not always, but most times it's confusing to students, is the melting point or boiling point. So they say, oh, wait a minute, so why is melting not making something new? Because if I melt ice into liquid, it's still water, right? I haven't made something new. It's H2O here, it's H2O here, it's H2O here, right? I haven't made something new. And so I have gold, and I melt it. It's still gold. It's just liquid gold, right? So I haven't changed the composition and turned gold into silver. That's what I mean, right? So I haven't changed the identity. So those are physical properties. So all these kind of things you can observe without creating something new. Now a chemical property then is just the opposite. So these are observations you make, but in the process, you have to turn it into something new in order to note that observation or to note that property. Can you think of one? What's something you could note about something in this room or whatever? But when you learn that, you had to change it into something else. Yeah, it's a little harder for this one, I would admit.
This room.
Oh, yeah, yeah, the room. I was thinking the room, but yeah, I don't care. Anywhere, I guess, yeah.
Would something being radioactive be considered a chemical property?
Yes, that would be, actually, yes. It does actually turn it into something else when it emits radiation. So, yeah, that's a good one. Well, okay, I was thinking about flammability, combustibility. Can you burn it? So yes, that's a chemical property. It's a chemical property because when you burn it, it's definitely not the same thing after you burned it that it was before you burned it, right? Does that make sense? Another one is corrosion, corrosiveness. Okay, so you might know, for example, that silver tarnishes. Okay, well, it was silver, but when it tarnishes, at the end, it's all green. It's not silver anymore. Now it's a silver oxide. You made something new. You might know that it reacts with oxygen and turns to rust or something. Again, you made something new. So these are all things where you do change the composition. It's not what it was anymore. Okay, I think you got that. So let's try a couple. So get out your handout, unless you don't have one. Then you should smack yourselves, remember, for next time. Okay, so quickly go through these 7 and tell me Is this a physical property? You can make the observation without it becoming something new, or a chemical property? During the process, you actually make something new. So, real quickly, just take your 7 guesses, and then we'll custom discuss with the neighbor. Seven guesses, write them down real quick. Okay, well, go ahead and compare with your neighbor whenever you're done and see what you guys think. See if you agree. If you don't agree, we'll talk it over. Help each other out. That's how we learn. Convince one another. What do you think? Discuss that one. Was it change it into something new when you... You got a copper wire, you pass electricity through it. Is it still copper when you get done? Yes, still. Okay, let's look at these. So, it is a silvery white, lustrous, or shiny. That means metal. That's definitely a physical property, right? You can make that observation without turning it into something new. It melts at 649, and it boils and turns to a gas at 1105. That is still physical, we just said, right? So you're not actually making it something new. All you're doing is changing it from solid to liquid to gas. So, okay? Has a density of 1.738 grams per cubic centimeter. Yes, exactly. Yes, you can measure the mass and the volume without changing it into something else, right? You can do the density. Okay, it burns in air. It gives off a bright white light. Now we've made something new, right? So burning things makes something new. Yes, that's definitely going to be a chemical property. Okay, it reacts with chlorine gas and goes from being shiny white and silver to being brittle and white. Yes, you definitely made something new, right? So that is a chemical property of this, whatever this mystery element is. You can take it and you can pound it out into sheets, or you can pull it out into wires. It's still just a physical change, right? You haven't actually changed it into something new. And you can conduct electricity through it, which is always the one that can, always one here. G's always the one who's kind of like, I'm not sure about that one. But it is still physical, right? So you pass electricity through a copper wire, it's still copper wire when you get done. It doesn't change it into something new. Okay, so my question is, anybody have an idea what this mystery metal might be? This mystery element. Yep, it's all the same thing. Nope, it's silvery white. The one that kind of gives it away maybe is D. It burns in white, gives a blindingly white light when you burn it. Good guess. Good guess. It does burn in water. No, potassium. Good guess. Actually, it's blindingly. That's a very good guess too, but it's not. That's not a metal. That's a non-metal. We'll see. It's used in flashbang grenades. It's used in road flares. It's used in fireworks because it's super bright. Nope, you can't burn lead and get it. It is. Okay. I'll give you another hint. Starts with an M. Magnesium. It is magnesium. And it burns, blindingly white light. It is super bright. Like I said, using flares and flashbang grenades and fireworks because it's blindingly white. Okay. So, now that was a physical chemical property. A physical chemical change is similar. So you can take your substance and you can undergo some kind of change with it. So first you're kind of standing back, just noting observations about it. Now we're going to actually do stuff to it. Well, there are things you can do physically, again, which don't turn it into something new, or there are things you can do chemically where you actually do turn it into something new. So what's an example of something you could do, let's say, to ice, or to that desk, or to your calculator, and you could change it, but it won't make it something new. So let's just say ice. How could I change that and not make it something new, though?
Make it water.
Yeah, make it into water, right. So I guess you could change the state, right. You can do a state change. How else could I change? Yes, exactly. You have to change the shape, right? I could cut it up and make it round, or make it into a lovely swan ice sculpture or something, right? I could change the shape. Yeah, things like that, right? Yeah. Yes, you change the size. You make it smaller, right? Cut up into little small cubes. Change the shape. Change the state, right? Now the other one you can do, which is not quite as obvious, is when something dissolves. So if you dissolve salt, let's say, into water, well, it's still salt. You haven't made something new, but it went from a solid to, to not really liquid, but actually to aqueous. It's dissolved. So yeah, changing the state, changing the shape, changing the size, dissolving things. Yeah, question?
Does it count if you change it to energy?
That would be a chemical change. You're actually making something new at that point. Yes, it won't be whatever it was, and now it'll be energy, it'll be something new. Yeah, so chemical change, yeah, you're actually making something new. So chemical changes are basically where we're heading here. Those are chemical reactions. So you take hydrogen gas and oxygen gas and you make water. So it's totally something new, different properties entirely. So chemical changes are chemical reactions. So now we're making something new, okay? You have a new composition in the end. You do not have what you started with. Okay. So now I already mentioned a bunch of this, right? Like I said, burning stuff, corrosion, whatever, different things like that. Oakley dokley. So, now I will say, this is not quite as obvious. So you might just watch something occur and say, oh, was that physical or chemical? So for example, let's say I mentioned putting salt into water. You might think, oh, must have made something new because it was a white solid, now it's a clear liquid. But there wasn't actually anything new that was made. It's still salt dissolved in water. So there are 5 things for you to watch for, and these will tell you, aha, it was actually a chemical change, not just a physical change. So the 5 things to watch for are seeing the gas being given off. Okay, so you put it into water or you mix it and it begins to bubble and fizz and give off vapor. That's definitely a chemical reaction. Now you're making new something. You're making a gas, right? It's not just mixing it up. You're actually making something new. So you're not just like mixing alcohol and water. You're actually making something new. Okay. Another one is gives off light, so it begins to glow or whatever, or gives off heat. So you mix it and it gets really hot. And the reverse, that's also true. You mix it together, let's say in a beaker, and it gets really cold. It absorbs heat. So a change in heat. Yeah, so if that happens, that's definitely a chemical change, not just a simple physical change. Normally. Another one is formation of a precipitate, which is a fancy word for a solid. So you mix 2 liquids and you get a solid. That's a definite chemical change. So here's a picture right here. As you see, here's a clear liquid, a yellow liquid, and it makes a cloudy yellow solid. So that's definitely a chemical change. You're not just mixing the liquids, you're actually making something new, right? And the last one is you get a permanent color change. So it was blue and now it's red. It was clear and now it's pink. So if it changes color, definitely made something new. It didn't just stay the way it was. Yeah.
When you open a carbonated soda, is that a chemical change since it's releasing?
That one is not. No.
Is that more pressure? Stuff like that?
Yeah, so all that wasn't really, but in that case, what it was is your soda was bottled with carbon dioxide, dissolved up in your bottle. So you got in here little bits of some carbon dioxide gas, and also some up here in the top of the container too. So when you open it up, all the extra just kind of flies out. But yeah, it's not actually making something new. Yes, yeah, good question. Okay, so your turn. So take a guess. Now the way to kind of figure this out, I always say is, okay, so ask yourself, is that process reversible? If it is reversible, it was just a physical change. But if you can't undo it, it was probably a chemical change. Or ask yourself, has it made something new? If it has become new, well then that's a chemical change. So take your guess. Can you reverse it? Has it made something new? That'll kind of tell you physical or chemical. Has it become something new, or can you undo it? Does it have the same properties, similar before and after? Okay, talk it over if you haven't yet. What do you guys think? These are a little sneaky sometimes, so make sure you agree. If not, figure out why.
Yeah, I'll think about
Okay, let's look at, so when you iron rust, is that making something new, or is it still the same thing before and after? It's something new, right? So it was a hard, solid gray metal, now it's flaky and orange, right? So it made something new, so that's definitely a chemical change, right? Okay, so B says you have some water, you put some sugar in it, and it all dissolves and it seems to disappear. Have you made something new? No, it's still sugar and water, right? Still sugar and water. You just mix them together. You've not made a new magical compound, right? It's still, so that's physical. How about you burn a log? That's definitely a chemical change, right? Yes, you cannot go back and get the log back, right? Probably not. Be a little hard. Okay, how about you melt some ice? It's still a physical change, right? It was water before, it's water after, so the same thing. How about you take a big stick of cinnamon and you grind it down into cinnamon powder? Still cinnamon, right? You haven't made anything new. Yes, this reminds me, there was a article I saw in the news like last week. Anybody else see this? With the eggs?
That's physical, correct? Or is that
Huh?
when they unboil the egg?
Well, they actually unfried an egg, I think, too, they said.
Yeah.
They were able to unfry an egg. It was UC Irvine and some scientists over in Australia. They were able to actually unfry an egg. So yes, frying an egg is normally a chemical change because you're making different compounds out of your proteins, you're rearranging them, but they're actually able to figure out how to break them back down and put them back. They unfried an egg.
So would it be
is that crazy?
Is there a video?
I don't know if there's a video or not. I've read the story, but it's pretty crazy. Yeah. Huh?
Where was it on?
I just saw it on Newser app, the little Newser app for your phone. That's why I just saw it on there. Yeah, I'll find the article maybe. I'll post it on Blackboard for you to see if you want to see it. Pretty crazy though. It's a breakthrough technology, ability to manipulate proteins and to recover proteins and stuff. It's really crazy. Okay, so we said we can change states. So when you go between a solid and a liquid, or a liquid and a solid, well, that temperature, of course, is called the melting point, right? So for water, that happens at 0 degrees Celsius, right? And the freezing point is the exact same temperature, right? So solid to a liquid, 0 degrees, or liquid to a solid, 0 degrees for water. Right, so same thing. Erase while you're writing here. Okay. So let me say, solid going to liquid, liquid going to solid. So solid going to liquid, that's called melting, right? Liquid going to solid, it's called freezing. How about going to a gas? Well, a liquid going to a gas, that's called vaporization. Or you can also, you might hear it called evaporation, and that happens at the boiling point. And then the reverse of that, when you turn it back, that's called condensation. So when a gas forms condensation on the outside of your Coke can, right? You see, the little drops of water. That's condensation. It's gaseous water turned back to liquid water. Okay. Okay. Now, whoops. Now the ones you may not be as familiar with, I just want to tell you. Solid going to a gas directly is a crazy one, okay? So you just totally skips the liquid, goes to a gas. Anybody know what that's called?
Sublimation.
Sublimation. You are on it. Yeah, that's obviously is a much more rare phenomenon compared to the other ones, right? But the example of that is probably dry ice. Right, you get like, I'm sure you've all seen dry ice at a Halloween party or something, right? You have your punch bowl with your big block of ice, throw in the punch bowl, and it turns from white solid to white gas directly, right? So that's called sublimation. Now the reverse of that's also crazy. It goes from a gas right to a solid. Anybody know that one? That's called deposition. Deposit, basically. Deposition. So example of that is frost. You go outside in the morning someday, and your grass was all covered in solid white frost. Well, that was deposition. Okay, so it wasn't like it went from a water vapor first to water drops, water solid. Nope, it went directly from water vapor in the air to water solid on your grass or whatever. Another one is in your freezer. You put in some frozen meat and you pull it out, it's covered in ice, right? When you pull it out. So that's also deposition. It went directly to a solid. Okay, well, let me show you this thing called the heating curve. It's kind of an interesting little phenomenon. So heating curve is a way of trying to represent how the temperature changes as the state changes. So, I'm going to erase this and make a bigger chart here on the board if we got that written down. So this way, we're going to look at the heat being added. So here's heat. I'm adding in my heat. This is my temperature. How's the temperature changing? Going this way, okay? So let's make it in Celsius. Let's just say degrees Celsius, whatever. Okay, so you're going to look at something like this. So let's just do water. Okay, water is an easy example. So let's say I'm down here and I'm at negative 20 degrees Celsius, okay? Well, obviously it's going to be a solid at that point, right? And then I add in heat to it, and it goes from negative 19, negative 18. It still stays a solid, right? Stays a solid until what point?
No.
Until I get to 0, right? So 0 is not. So stays a solid, stays a solid, stays a solid until I get to 0 degrees Celsius, right? So at that point, now it's going to begin to change from a solid, I'm going to put solid right there, to a liquid, okay? So this right here will be the melting point, right? Or the reverse, the freezing point. I'm just going to put MP, melting point, right? 0 degrees Celsius. Okay. Okay, and then now here's the interesting part. While it's melting, it doesn't change temperature. Notice this, I have this little flat part here. So you get ice and it's melting. As long as it's still melting, still melting, still melting, it stays at 0 as long as it's melting. Once it has all been broken apart, because it was all in a big clump, right? And they were all locked into place. They're in a solid, right? Well, once you kind of break apart all the little connections that were holding them into place, and they're all begin to move freely, it's all liquid, then it begins to heat up at that point. So then you add more heat and it gets hotter, 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 hotter until you hit 100 degrees, which is the boiling point, right? And then at that point, now they begin to fly apart into the gas phase, right, and really separate. So same thing though. While it's boiling, it stays at 100 degrees. So this here would be melting going this way, right? And the reverse would be freezing going the other way. It's a little small for you in the back, sorry, but it just says right freezing. This way would be evaporation or vaporization. And the reverse is condensation. So this is why, let's say you're boiling water. If you're boiling water, it's always going to boil at 100 degrees. You can turn up your stove as hot as you want. Your food will not cook any faster. If it's boiling at 100 degrees, it's going to stay at 100 degrees. Okay, so like I said, you can crank it up as hot as you want, but if it's boiling, it stays at 100, right? So it can't boil above 100. So as long as you still have liquid turning to gas, it's going to stay at 100 degrees. Okay. Now the reverse is just called a cooling curve. That's just kind of the exact opposite, right? So imagine it going the other way now. Steam cools off once it right. So once up here at 120, it gets to 100, and now it turns to liquid, and it condenses. Then now it's a liquid. Liquid cools off until it hits 0, and now it begins to freeze. And it's all frozen, then it goes colder. So just the reserve, okay? So that's just showing the heat removed. Okay. Some of you still scribbling, so I'll wait a second here. Okay. And I already told you, right? Sublimation, and deposition. Okay. I did it twice. I don't know why. Okay, well, here is an interesting phenomenon I want to discuss. This is kind of a cool thing, I think. Pardon the pun. It's called specific heat of a substance. Oh, I'm sorry, what did you miss?
What was the opposite of heating curve again?
Cooling curve. Yeah, cooling curve. Okay, called the specific heat of a substance. Let me check something real quick. Do I have a slide for this thing? I do not. Okay, so I'm going to. Okay, so back up then. I'm going to make something kind of cool about this. Let me give you just real quickly, just for a little added bonus, a couple of some uses for this. Why this is important. Why you should give a crap. Okay, have you ever seen this? I used to live for 3 years prior to this, up in Fresno. Around Fresno, there's all kinds of orchards and fruit trees and vineyards and stuff. And it would get like a little bit cold at night, and they were calling for a frost. They would turn on their sprinklers. They would like spray down the crops with water all night long. I was like wondering, why are they putting water on their crops when they know it's going to freeze? Do they want to turn them to ice? And the answer is actually they do want them to freeze. So why do they want them to freeze? Well, the farmers are smart and they know their chemistry, and they know that the danger zone for most fruit is when it hits -2. So -2 is the point when your fruit is getting damaged. So their goal then on their blueberries or oranges or whatever is to not let it reach -2. So what they do, like I said, then on their farms they spray them down with water all night long. They spray it with water, spray it with water, spray it with water. Okay, so let's say it's daytime and it's 10 degrees and begins to cool off at night and it hits 0 and the water on the fruit begins to freeze. But while it's freezing, what happens? It stays at 0 degrees. As long as there's water freezing, it's going to stay at 0, stay at 0, stay at 0. And the outside air might go down to -1, 2, 5, 10. But as long as there's still water freezing, it keeps it at 0. So yeah, very clever, I think. And the other thing that happens is this way, when you're melting, like I said, so when you're melting things, you have to give it heat. But when things are freezing, well, now they have to release heat. So what also happens then is while the water is freezing, it's actually releasing heat into the fruit. So it's actually warming the fruit, and it keeps it at 0 degrees. Yes?
Why is it kind of the same thing or the opposite when they turn on the heaters, like vineyards, they'll have the heaters on between the vines so that they won't...
I guess it's a similar kind of thing. Maybe the temperature range is a little lower than 0 for grapes, so maybe they can't get down below 40 or something. I don't know, or 20 or whatever. Yeah, I don't know. Yeah, maybe that's the difference. Yeah.
So ice can't get colder than 32 degrees.
While it's in the process of freezing. Yeah, so once it's frozen, then it can go as cold as you want. But yes, as long as there's actually still liquid turned to solid, it won't go any colder. It won't go any colder. So they keep running the sprinklers all night long, so there's always fresh water to be freezing. If they ever stopped that, then it would eventually freeze, then it would get too cold and ruin the fruit. So they keep spraying fresh water all night long. Oh, those smart sons. I'm farmers, right? Those smart farmers. Okay. So specific heat is an interesting property. It's kind of fascinating, I think. And it's different for every substance. So it's different for water, copper, gold, whatever it is. It's different for every substance. And it's basically the amount of energy it takes, the amount of heat required to raise 1 gram of a substance 1 degree Celsius. And this sounds a lot like, remember on last class I mentioned a calorie. And I said a calorie was the amount of energy that it takes to raise 1 gram of water 1 degree Celsius. So water specific heat is 1 calorie, or 4.184 joules. But again, every other substance has a different amount of heat required to raise 1 gram of it 1 degree C. So most things we'll see take far less heat to actually heat them up. So they heat up much easier, okay? That's called the specific heat. So the equation we like to use is specific heat is equal to the heat divided by the mass times the delta T. So that little triangle is the capital Greek letter delta. Whenever you see that symbol, that capital triangle thing, that means the change in temperature. So make a little note to yourself. So if you see delta T, change in temperature. Delta P will be change in pressure. Delta V will be change in volume. Okay? Now, another way you see this equation written, I want to show you, is using variables. You'll see capital C equals small q over m times delta T. And this just means the specific heat capacity, C. And Q is a symbol for heat, and M is a symbol for mass. So it's the same thing, but I'm just going to warn you, you may see it written with actual variables instead of words. So this was all figured out by a man in Edinburgh, Scotland, named Joseph Black. So when I was in Scotland a few years ago, we went to the university there. There at the University of Edinburgh. I met them with the chemistry department, and the chair was showing us around the chemistry department. And Joseph Black, he was the previous chair back in the 1700s. It's kind of a crazy little thing. So in her office, and she had a big line of these old chairs, and they were actually the previous chairs of the department. They're actual chairs. They had a line of old chairs belonging to the previous department chair. So she had a bunch of chairs. And then each chair had like a little picture on it of the previous chair, and she actually had Joseph Black's chair. I thought it was kind of interesting. So there it is. So there's Joseph Black's chair when he was the chair at the University of Edinburgh Chemistry Department in 1766. So there he goes. His butt sat right there in that chair 250 years ago. So there you go. So that was kind of a crazy picture, I thought. But anyway, so the units then are going to be heat over mass times temperature. So something like joules over grams times Celsius, or calories over grams times Celsius. But that'll be your units, because how much heat do you have to put in to raise the temperature of this thing? So joules per gram Celsius or calories per gram Celsius? Yeah.
What's the difference between heat and temperature here?
Okay, remembers the difference between heat and temperature. Does anybody recall the difference? Temperature is what? It's a measure of what? I failed as a professor. I can't believe it. Oh my gosh. It's a measure of the average kinetic energy. Yes. So what's the average motion of those particles? What is heat?
Transfer of energy.
Actually, the transfer of energy, right? Right. So remember, I said if you have a little small glass of water at 90 degrees versus a giant bucket of water at 90 degrees, same temperature, but that bucket has a lot more heat to transfer than that little glass of water has. So heat is not the same as temperature we talked about. Okay. So here's a list of a bunch of different substances. So I want you to notice water has a freakishly high specific heat. Water, in fact, is about the high specific heat of anything in the universe. It's pretty darn hot. I mean, not hot, high. So, what does that mean? Well, that means it takes more energy to heat up water than it does anything else. Water is the hardest thing to heat up, basically. Water is way harder to heat up than aluminum, copper, gold, ammonia, alcohol, ethanol, anything else. So, if I have 1 gram of water, it takes, I got to pump in 4.184 joules to make it go up 1 degree Celsius. But if that was alcohol, well, it's only 2.46. If that was gold, it's only 0.129 joules, right? So it's 40 times easier to heat up gold than it is to heat up water. Are you with me? So this is a very important thing. So this is one of the reasons why scientists, actually, they're always looking for water, presence of water on various planets, because they know water is so important, not just for drinking, but also because of this very thing, specific heat. So let me just tell you a little quick thing here, why we care. So let me draw a lovely picture of our fabulous planet right here. So I'm going to draw. So here's planet Earth, okay? Here we are, planet Earth. So here's North America. It's going to be a really crappy picture, sorry to say. Okay, so here we go. Awesome. You are here. Okay, so we're right there, right? So now around us though, on the Earth, mostly we have what? Lots of water, right? We've got big, giant oceans full of water. So the Earth is mostly water. Okay, well then around us, you might know, out in space, we have this giant ball of fire in the sky called the sun, right? It's a big red fried egg, apparently. And it beats down, and it zaps the Earth with megajoules of energy every single day. So why doesn't the planet's temperature just go shooting up hundreds of degrees every day? It's because we have all of this water around. And like I said, water is the hardest thing to heat up. So for every 1 gram of water, you got to put in 4.184 joules just to raise it 1 degree. And we got bazillions of grams of water all over our planet. So yes, it takes a lot of energy to raise our temperature range, right? Right? So yes, our temperature range then, is pretty constant, right? Right, on the planet Earth. But let's say you go over here though, over here then let's say, over here somewhere, and it's Palm Spring Desert, or it's something like that. Well, now there's not much water around. Well, now what happens? Well, now then during the day it does get a big spike, right? It gets really hot during the day, and it gets really cold at night. Right, but here in San Diego, well, there's ocean right around us, so it's a much smaller change in temperature range. Does that make sense? Because you have all this water nearby, which is why we love it here, right? Because you have that nice temperature range. That's why I moved here last year. So yeah, okay. So it's also important for us as people. So I will draw a portrait. I'll draw a nice self-portrait. So here's me. Skinnier here, I guess, than I am in real life, but here I am. Okay, and here's my hair. So I have a nice. Maybe if I get my hair.
Why is your hair on the floor?
I don't know that. That was an accident. It was my finger. I have a little beard right here. Okay, so here I am. So same thing happens. Okay. So our bodies. Okay, I'm gonna erase. That was an accident. It was my pinky was laying on the thing and drew it on the ground. I didn't mean to do that. Yeah, my hair is falling out. Maybe that's what I meant. I don't know. So I need a face. Okay, I'll give myself a face. Okay, so I have brown eyes. There you go. And I'm very happy to be teaching chemistry. There we go. Okay, so I have the sun is beating down on my body all day long. Rarely, though, obviously, because I'm very pale. But it does beat down on my body. And our bodies are mostly water, right? So that means, right, for an average person, our body temperature is 98.6 degrees Fahrenheit, right? Or about 37 degrees Celsius. Okay, so think about this for a second. If your body is mostly water, and you spike a temperature, and let's say it goes up to 39 degrees Celsius. Why are fevers such big deals? Well, the reason is that means there must be a ton of extra energy being given off in your body. So, just for example, let's say, an average person weighs 70 kilograms, okay? Well, that's 70,000 grams, right? So to raise 1 gram, it takes 1 calorie, right? To raise 70,000 grams, it takes 70,000 calories. If I want to raise it 2 degrees, Now it takes 140,000 calories. So that means something's going horribly wrong with this really handsome guy right here, because he is producing or burning 140,000 extra calories all the time. So something is going wrong with his metabolism. Are you with me? So yeah. Okay, well also, so what happens, okay, so normally then what happens, right? Right? You know, sun beats down on you all day long, and your body temperature stays at 37, right? So you don't suddenly get, like a big fever of 45 or whatever, right? It stays around 37. Well, why does it stay around 37? Because you're made of mostly water, right? So the heat comes out of the water, and the water just absorbs it with no change. Or you go outside and it's freezing cold, but your body temperature stays at 37 unless it gets really, really cold, and then then it goes down at that point. Okay, so what if your body was made up of iron, and you're like a robot? Okay, what happens now when the sun beats down on you? Well, let's look here. So iron is roughly 10 times easier to heat up compared to water, right? So now you go outside as a robot and sun beats down on you. Now your temperature does suddenly shoot up really hot, right? Or if it's cold, it suddenly shoots down really low. Does that make sense? So yeah, that's why water is important to us, why it's important to our planet. You all learned so much today. Wasn't that the best thing ever? Okay. So, and there's this chair again. Okay, so let's try a calculation or two. And let's try a couple. So let's say we went to the lab and I gave you an unknown metal. And I said, okay, here's an unknown metal. You tell me what the metal is. One way you could do that is you could figure out, okay, what's the metal's specific heat? How easy is it to raise or lower? And you go back and say, aha, the metal was 0.452. It must be iron. Or aha, it was 0.129. It must be gold. So you can figure it out based off the change in specific heat. So what you would do, I'll just draw you a little picture here, just kind of illustrate what's going on in this calculation. So let's say you have a nice little thermos, so there's no heat escaping out, and you have some water in here, and you got a thermometer. I'm actually do this in lab. I think is this next week's lab, measuring specific heat. It's not next week, it's the next week. Maybe it's the next week, but one of these next week's lab. 2 weeks. So 2 weeks first you're going to do this. So you're going to take it, okay, you measure it, and it's at 20 degrees Celsius. Okay, so you get some water, the heat, and you throw it in, and now it goes to 24.5. Aha, so how much, so it took 65.7 calories to raise your metal from 20 to 24.5. So let's figure out what is the specific heat. So we're going to plug in here. Just plug into our calculation here. So we're trying to find variable C, the specific heat capacity, technically. Take the specific heat capacity. So we need to know the heat, the mass, and the change in the temperature. So I didn't have myself any room to write on this, but I'll try and do it anyway. I'll do it here on the bottom, I guess. Okay, so Q equals, try that again. We're doing C equals Q over M delta T. So what is my Q? What's my heat? How much heat was there pumped into it? How much heat was pumped into it? 65.7 calories, right? Heat will always be calories, joules, something like that. We're going to divide that by the amount, the mass. What mass of metal did I use? 24.8 grams. Okay, now we're going to multiply that by the change in temperature. So, whenever anything is the delta, the change, it's going to be the final minus the initial. So I'll make a little note for that up here for you. So delta T equals T final minus T initial, okay? Final minus initial. So in our case, what's the final temperature? Where did it wind up at? 24.5. Minus the initial was, where did it start out at? 20.2. Okay, so let's punch it in our calculators, see what we get. So our delta T here is what? 4.3 degrees Celsius. So first I want to turn calories into joules. So 38.5 calories. Let's turn that into joules. So 1 calorie, it told me, was, remember that one's exact. That's one of the exact ones. 4.184 joules. So, got my calculator. Lose a ruler on the way. Throw it on the ground. So, 38.5 times 4.184. 161.084. But that should have how many sig figs really? Okay, but remember though I told you if you're doing multiple calculations, don't round to the end, right? So I'm just going to mark it at 3 just to remind myself it's really there. But I'm not going to round it yet. So if you want that, you can just keep 1 extra or keep them all extra, your choice. But keep at least 1 extra. Okay, so now I got to plug it into my formula. So I got to take C equals Q over M delta T. So Q, we just found, was 161.084 joules. Mass was 25.0 grams. Delta T, it's always the final minus the initial. So the final was 58.7. The initial was 31.5. So, let me just check this one first for my sig figs before I go on. So, what'll that be? 27.2? That was really messy. I apologize. I'll try it again. 27.2. So the reason I do that first is so I can see how many sig figs is in that, right? So now it's 3 sig figs on top, 3 sig figs in the mass, 3 sig figs in the temperature. So the answer is 3 sig figs, right? So I got 0.237. And what's my units? Joules over grams Celsius. You are so right. Okay. Okay, let me see where we're at here in the old lectures. Are we scheduled to do this next Monday and Wednesday? Or just Monday? What's that in your schedule? Have a schedule?
Just Monday.
So what's Wednesday?
Exam.
Okay, exam. Okay. Okay, so let's do a little more of this then so you can practice this over the weekend then, before the exam. So I was making sure because we still have 5 minutes left. So the other way to rearrange this equation is like so. Q equals mass times delta T times C. Same thing, I just rearranged the equation. So really, we could solve for any variable. We could solve for the heat, or we could solve for the mass, or we can solve for the change in temperature if we knew the other 3 pieces of the puzzle. So we could do any of those. Again, so I'm showing you with the variables you may see. Okay. So how much heat's going to be gained or lost? Well, it's based off the mass, right? How much did you use, right? The more you use, the more heat it'll either lose or absorb. Going to be based off, okay, so how much then was the temperature change by? Did it change 1 degree, 10 degrees, 100 degrees? And then what is the specific heat of the substance, right? Is it water? Is it gold? Is it aluminum? So all those things will affect how much heat are either absorbed or how much heat is released. So it's based off all 3, mass, delta T, and specific heat. Okay, I'm going to go on. You can write that down later. It's on the PowerPoint. So let's just try one before we're out of time. So let's say you have a hot water bottle it contains 750 grams of water at 65 degrees. Okay, so you take that hot water bottle and you put it on your bad knee or whatever, and it cools off from 65 degrees down to body temp, 37 degrees. Okay, so it cools off the water. How many calories of heat were being transferred out of that hot water bottle? So which variable am I trying to find? Q, M, C, or delta T? How much calories of heat? I'm trying to find Q. So we're going to solve for Q. So we've got Q. I'm going to put it on my little whiteboard, but you have to tell me all the numbers then. So Q equals M delta T and C, right? Okay, so what was the mass of the hot water bottle? What did it say? How much? 250 grams? That's what I thought. I thought 750 grams. That's what I was thinking. Okay, delta T. The change, the final minus the initial. So what's the final? Where did the hot water bottle wind up at? 37 minus the initial. It was at 65. Okay. And what's the specific heat of water? Is it? Yeah. What did it tell you in the problem? Does it say in calories or say in joules? What does it say to do it in? Does it say? It says calories? Okay, so use the calorie one. The calorie one is 1 calorie per gram degrees Celsius. So I'm going to solve this little delta T right here. What's 37 minus 65? Negative 28, correct. So, grams cancels, Celsius cancels, I'm left with calories, which I should be. So you punch all that in there. And let me see, 750 times negative 28 times 1 calorie. Negative 21,000 calories. Let's check our sig figs real quick. How many sig figs are in 750? 2. How many are in negative 28? How many are in a calorie?
That's exact.
That's been defined to be true, right? A calorie has been defined for water. That is exact. You are correct. That's been defined. So the answer should have how many? So how would I write that with 2 sig figs? Yeah, 21,000. Or I could write it 10 to the 4th calories. So I was having a discussion here earlier. What does the negative sign mean? It means heat was lost, right? It lost heat, right? It started off hot and got colder. It lost heat. Okay, so I'm going to tell you this again. The number one reason people do not pass this class is they don't practice it often enough. So I know your exam's not till next Thursday or next Wednesday, but don't wait till Monday or Tuesday and do all the homework. Do some homework today or tomorrow. Do some Friday or Saturday. Do some Sunday or Monday. Email me questions. Go to the Library Tutorial Center, right? Get some help. You need lots of extra practice. Cramming does not work in this class. You need lots of practice. And if you did miss some ones on the first quiz, we'll figure out why you missed them and go practice those same ones again. There are extra practice problems, remember, online too. So you can do so go back and do extra ones on chapter 1 if you missed them, right? Do extra ones. And even if you did them late and you on the homework, right, go back and do them again. You can get still late credit for the ones you might have skipped. So there's no reason to ever have any undone. So always get at least partial credit. So get all the points you can. So. Okay, we'll see you on Monday. Yes. No, there wasn't a quiz because we finished it Monday. It's due Wednesday, but our exam is Wednesday, not our quiz. Let's have an exam instead.